Welcome everyone. So today we are going to discuss about large scale storage solutions from SMA. So in SMA we have 40 years of experience, which will have portfolio in all the segments in solar, including home, business, commercial, as well as the utility segments. So in this entire segments of PV as well as storage, today we are going to talk about this large scale storage applications, which is used for utility scale. Example, where you have medium voltage grids or high voltage grids with the battery storage applications. What type of products we have in SMA, what type of applications it is all supported, what are the advantages of DC AC coupling. So all this we'll discuss today. Please feel free to write your questions in the Q&A sessions. So first, we'll start with the SMS experience in large-scale storage. Our first hybrid applications. We started in 1987 with wind diesel hybrid applications, and then we started further development towards integration to the renewable energies to the grid. And our major breakthrough happens in with Sunny Island, that we started with 1999. So almost 20 years, more than 20 years from now. As you know, the Sunny Island is still available with a lot of major updates and everything, but the platform remains same. So it's a proven product with the 10 years of warranty. This is Sunny Island, used for residential as well as commercial applications for the battery. The same applications has been improved as well as updated for the large scale, like grid forming, grid smoothing, power smoothing applications. Everything are possible in large scale. So our first large scale applications in storage happened in 2011. This is our first project in 2011. And then we also launched higher capacity storage inverters, like Sunny Central storage in terms of CPXA platform, starting from 500 kilowatt to 1 megawatt in 1000-volt systems. And then we upgraded further to our bigger inverter platform, starting like 2.5 megawatt, 3 megawatt, and now finally we are in 3.95 megawatt series. So this is how our evolution of storage happens in our company. So giving you a key numbers, we have more than 50,000 installed bases in all over the world in storage, only in storage. And in terms of storage, the experience is around 20 years. So out of 40 years, 20 years we have experience in storage. One of the key examples is Sunny Island, which you've seen is having a experience itself is more than 20 years in that. And 450 people are working only in storage products and storage applications in SMA. And in terms of installed base, we have 4+ gigawatts, more than 4 gigawatt, more 4.5 gigawatt for now in large scale storage applications. Okay, so let's start with the product portfolio. In large scale storages, we have two types of batteries. So the battery voltage defines which type of inverters can be used, similar to the modules. In the PV module, we have 1000-volt or 1100-volt module technologies was there. And now for last 3 years, we have seen 1500-volt technology PV panels in the large scale applications. Similarly, the storage also has this kind of segments, 1100-volt or 1000-volt segments, as well as 1500-volt segments here. So in 1100-volt segments, we have inverters starting from 1.9 megawatt to 2.5 megawatt inverters. And then for the further higher capacities, we have in 1500-volt technologies. Similarly, for the same storage inverters to be connected to the medium voltage grid, we also have MV stations, like transformer with RMU stations, where you don't have a local manufacturing possibilities. There you can consider our medium voltage stations as well. Plus, we have DC-DC converters for the DC coupled systems, which will be used along with our PV inverters. This will also be covered in detail. And the another important product we have is a hybrid controller. It is like an energy management system or PV management, PV plus storage management system, which will do the complete integration of renewable energy systems along with the diesel and as well as the batteries for the smooth power operations. So first, we are going to discuss about the storage inverters. So as I mentioned, there are two test applications. One is 1000 volt as well as 1500 volt. So here you will see an inverter starting from 1.9 megawatt to 2.9 megawatt on 1000 or 1100 volt applications on the batteries. This is very critical. Based on the battery voltages, these inverters will be decided. Similar to the MPPT operating voltage, how we have in the PV inverter, the same criteria of MPPT operating voltage window is also available for storage inverters. So it is very important to match the battery voltage window with the inverter operating window for the various different temperature profile, including the reactive power compensations and all the scenarios. And for 1500 volt applications, we have inverters starting from 3.4 megawatt to 3.95 megawatt in 1500 volt applications. So this 1500 volt is a maximum system operating voltage. So minimum maybe with 850 or something like that, or 900 it will be there, but the maximum is 1500 volt applications. Similarly, we have also have XT series in the 3.4 to 3.9 megawatt. This will only differences, this will have higher discharging capabilities, that it can discharge more power from the same inverter capacities to support the grid. So some special applications, especially the grid forming or as well as grid supporting high grid support applications, we will need this kind of a high discharging power for a shorter durations. So this is possible from our Sunny Central Storage up XT platform. XT is for the extreme power. So in 1000 volt or 1100 volt system, this is 1.9 megawatt to 2.9 megawatt inverter series. You will see a major difference in the electrical parameters. Is the AC operating voltage window. It will AC operating voltage will keep increasing. Similarly, the minimum MPP voltage will also change. So it depends on the battery operating voltage window. We can select which type of inverters and as well as the project capacity. We can decide number of inverters needed for this project. But the advantage is these inverters, what you see here, is same as our PV inverter platform. So in terms of service, in terms of product design, life, and everything are based on the PV inverter platform. And as you know, our inverters are designed for 25 years, and we also offer warranty for up to 25 years. The same can be offered also for storage inverters. So this will also help as an investors or as a plant owners to reduce the risk in terms of securing their futures for the products. And we also have the same product portfolio certified for UL for the US grid requirements. So in 1500 volt, similar to 1000 volt, we also have 1500 volt platform. So here, this is also similar to our PV inverter platform. So we also have Sunny Central up inverters in PV, which is starting from 4 megawatt to 4.6 megawatt. So it's the same platform. So DC inputs are different, but you will see the AC voltages are same. The MPP voltages are almost same. So we try to maintain a same portfolio for PV as well as storage for the further easier support as well as to have a stable product for longer durations. So this will help us as a SMA to support you for the warranty extensions. It's a very key for a storage applications. In PV, the difference is there is no communication happening between the PV module as well as the inverter. It was not needed. But in storage, there is a BMS from the battery, which is supplied by the battery supplier. So it is very important that BMS and the PV inverter, storage inverters works parallelly and communicates to each other. If there is any issue in the inverters, then if the inverter needs to be replaced, the communication needs to be redeveloped. And this further communication testing has to be done. So it is not possible. Let's say the battery technology keeps changing. So after 10 years also, the same battery communication and everything will be available. So, so whoever the battery projects you want to do, people will always try to go for a warranty of minimum 10 to 15 years to cover up this risk, because the battery life is 10 to 15 years. So the entire duration, there is no risk of changing the inverters. It is not easily possible, similar to the PV inverter. So that is why the warranty is very key, very important role in selecting the inverters, especially in storage applications, because of the communication between battery and the storage inverters. So we also have UL certification for the same platform. It is called US model inverters. So here you can see 3.4 megawatt at 3.4 megawatt at 25 degree, and at 50 degree it is at 2.88 megawatt. Similarly, the highest capacity 3950 up inverter, where the maximum power it can generate at 25 degree ambient temperature is 3.967, and at 50 degree it is 3.310. As it is an outdoor inverter, it is true outdoor inverter, there is no difference between ambient temperature as well as the degrading temperature considered by the our inverters. When I explain the cooling of the inverters, I will explain you how the temperatures are measured, but this degrading will happen based on true ambient temperatures only. So there is no need to consider any delta T for or the differential temperatures in your analysis. So the AC voltage is 690 volt for the biggest inverter, and the smallest inverter in 1500 volt is 600 volt is the AC operating voltage window. So the same platform, we also have higher capacity power for discharging. So only difference is these inverters have the higher capacity discharge. So not there are two way. This storage inverter has two ways of feeding the power. One is charging and discharging. So charging power is always limited to 3.4, but it can discharge up to 4 megawatt when the support is needed for the grid. Like for example, black start functionalities to support the interest currents, or as well as certain grid inertia support. So for this kind of applications, we will need this high discharging capabilities because the storage inverters take care of the complete grid. So it acts as a substation to support the entire grid. So the entire load has to be stable operating without disconnection. So in case of sudden fluctuations and everything, this discharge power will kick in to stabilize the load. So this is about the about the storage inverters what we have. So we'll deep dive into the product, how it looks like. So this is the storage inverter what we have seen. It looks exactly same for 1.9 megawatt to 3.95 megawatt. It's the same dimensions and same size. So this is an outdoor inverter, which is proper outdoor inverter. So no need to mount any sheet or any control room for these inverters. Nowadays, the batteries are also available for outdoor applications. Transformers will be outdoor, so entire system will be properly outdoor. And compared to the PV inverter, the difference is the PV inverters are spread across all over the PV field. That means maybe one or two inverters in a single station connected to the transformer. But in storage, the batteries, storage inverters, everything are kept in a single location like a substations. And it will be feeding the power to the grid and supporting the grids. So here we have a DC connection area in the bottom where the battery cables coming from the battery containers will be connected to this section. And here we have the DC protection area. DC switches will be here. And we have cooling fans inside the inverters. And this is the air outlet. And the air is taken from the top. It's a pattern of cooling concept of SMA proven. And we have been using the same cooling concept for almost 15 years for now for all outdoor applications. We have not changed it. That means it's proven one. and we have DC AC breaker switches for on and off the inverters, in emergency switches, everything available on one section. And this is the communication area where the communication devices will be installed, like a SCADA, like fiber optic switches, and everything will be installed here, MANA switches including that. And we have AC breaker, yeah, circuit breaker on the AC side, which will protect the inverters, and which will be controlled by the inverter firmware for the safeties and other regulation point of view. And the output connection is a busbar type, so from the inverters to the transformers connections here on the bottom. And here we have stacks. The bigger inverter, if you buy, it's a 3-stack version. So 3 stacks is placed inside the inverters. And we have auxiliary transformer inside the inverters to self-power this inverter. So no need to provide any external power supply. Only in case of black start function, the external power supply will be needed from the UPS. So for that kind of projects, we will provide a separate guidelines on how this has to be done, but it is possible. So only difference in case of black start function is required. So this is how the inverter will looks like. So here is a 3 stacks. These are 3 stacks here. So for example, if you're buying 3.95 megawatt inverter, each stack power will be divided by 3. So the power will be equally divided, and it is completely encapsulated around inside the stack area. The external air will never go inside, so that means no dust inside the inverter. We have a choke and other heating elements, including auxiliary transformers, or in the last section on that before the air outlet area. This is the AC breaker. Similar to our PV inverter, the entire architecture is same as our PV inverters. So we also provide 2400 volt IGBTs. That means 2 into 1200 volt IGBTs for 1000 volt, 1500 volt applications, and for 1000 or 1100 volt applications, we provide 1700 volt IGBTs. This is simply because when the inverters are forced to operate towards higher operating DC voltages, example 1400 or 1350 for longer duration, the IGBTs will have longer stress. It is the nature of the IGBTs to have failure, so the failure rates will go higher. So typically in 25 years, if the IGBT is supposed to have a lifetime to be replaced in one time in a year, but if they are not using this concept, if you reduce the IGBT voltages and reduce the gap between the operating voltage as well as the maximum IGBT voltages, then the IGBT needs to be replaced more frequently, maybe 4 times in a 20 years of lifetime. So this will increase further cost and replacement schedules, and also increase the failure rate. So to avoid that, as well as to have better life on the inverters, we provide higher IGBT voltages. The same concept we are also following in the PV inverters. And this will also help to provide continuous support for the grid without any disconnections. If this option is not available, the storage inverter needs to disconnect within 10-15 minutes if it is operating towards higher DC voltages. Then the continuous support for the grid is not possible. There are limitations for that. So all this can be overcome by this higher DC operating voltage on IGBTs. So here we can see a stack fan. This is a 3-phase stack fan for the cooling the entire inverters, and it is so powerful that if you put a dust or sand here on the outlet area, it will clean the entire sand and dust over there. They're so much powerful that the fans are. It will not allow any dust into the inverter. It will push all the dust coming from the top to bottom, and it will push it out. So this is the cooling mechanism. So we call it as opticool concept, the patented technology of SMA. This concept of cooling was introduced in 2009 with our outdoor inverters in the PV, which is called 500 CP inverters, semi-central CP. So from 500 kilowatt to 4.6 megawatt. For all inverter platform, we use the same cooling concept. It's a air-to-air heat exchange, but the mechanism what we use and how the products are designed by keeping the components in the right place, the coolings are done. There is no liquid cooling here, so there are no complications of leakages of liquids or the pump replacement or nothing. It's very simple air cooling mechanism, and there are two types of cooling it happens. So maybe you can call it as dual IPs. Yeah, so there are two types of chambers. One is the chamber where the external airs are allowed to pass it on for the cooling. The another chamber is where the only the internal airs are keep circulating, like sensitive components area, so that the external air will never come into the picture. Like shown in this picture on the left side, so you will see the fans on the DC side area. There are two small fans, single phase fans on the DC side area, which will keep circulating the air. So it will pump the air from the top to bottom, and then it will pass it on inside the stack area, and then it comes back from the top section. Again, it's recirculated. On the top section, what happens is there's an external air flow from here, and it will pass it on to the another chamber like this. So when the heat top from the external air flow is happening, there's a heat exchange. So this internal air gets cooled. So then and in this way, there is no external air going inside the inverter or in the sensitive area. That means no dust, no cleaning inside the inverter is required. And for the external airflow, this will be passed on through this narrow area, and through this stack fan, through this high power fan, this will be passed again between the stacks. So the space on the airflow is reduced so that they create high pressure with the help of radial fans, and then it will pass on between the stacks. So what happens here is the space gets reduced. So this will create more pressure so that the hot spots which are going to form inside the inverters will never happen. There's no possibility of forming the hot spots, so that the life of the components are not getting affected. The heated air will keep going out from the top to bottom. And we follow the top to bottom approach, and this been followed for almost from 2009 when we followed CPX inverters, simply because these inverters are installed outside. So when there is dust going inside the inverters, it will be passed on from top to bottom, and it will be cleaned out automatically with the help of gravity. So you may be seeing from other inverters where the air is taken from the bottom to the top. The issue is only the heated air will come out, but dust will not be cleaned automatically, which will end up in replacing the filters or clean the inverters regularly. So which will have more maintenance, more OPEX cost, plus the life of the inverters will keep affecting, and you will end up in replacing the inverters on 10th year, for example, or 12th year, because of the effect on the component qualities. So first, the important factor in terms of battery storage application is the communication, because the communication is a very key for the entire operations, starting from the battery still to the PV inverter as well as to the controller. So all these communications will happen through Modbus TCP/IP, except the communication between the battery to the inverter. It is usually through a CAN communications because of the BMS communication models. So here you will see why we are using Modbus TCP/IP is the communication speed for the Modbus is up to 100 MB per second. So if you use RS485 PLC, the communication speed is only 100 KB per second. So the controlling is not possible completely, and as there will be an issues in terms of controlling, and inverters cannot respond it on a fast durations. The key for the battery application is the response time. So in terms of our applications with the Modbus communications with the Ethernet cable, the response time you can see for the complete settling, that means receiving a signal till up to the complete response getting stabilized value is within 200 milliseconds. And imagine that how many inverters will be there, and so many controlled frequency signals will be keep coming again and again, including the response, including the acceptance of the response. So all is including that we cannot use RS485 PLC communications, and you cannot mount the inverters so far away. So that is why the inverters became in storage applications. We always use bigger inverters like centralized inverter. We don't use string inverter concept for the large scale applications simply because it's not possible. It's not worth at all. And the next important point is a medium voltage station, wherever okay, the storage projects can be installed in anywhere. Like for example, it can be used in any island applications, because that's where it's very important for the initial stages to support the grid and forming the grid and other applications. So there possibility is there won't be any local manufacturing of transformers, RMU, or it's not possible to get a good quality of transformers immediately on a short durations. So that's where our EMV station comes into the picture. We provide the same EMV station also for the PV. So the same platform is available also for the storage, including 20 feet or 40 feet containers, as well as the bigger capacity inverters. So based on the inverter platform, what you select, we provide the MV station. We provide the recommended MV station to the customers, including based on the type of the grid voltages, either 11 kV, 22 kV, or 33 kV applications. And these MV stations will have a transformer, RMU, auxiliary transformer for self powering the entire station, and it's a completely outdoor, and it's a finished station from our factory in Europe, and then it is shipped to site as it is, and just connect the battery cables on the inverter and the MV cable. So no assembly is needed at site. So that will completely take the risk of assembling a site and then doing a retesting and everything. It's completely not needed, and the entire station is shipment certified stations. So that means it's completely packed and it comes to the site, unpack it, mount it on the plinth, that's it. And it's an outdoor stations. So no assembly, nothing to be redeterminated, no testing is required from our side for commissioning the station. So it's approved plug-in play stations from Europe. The another important applications which are coming up now is the DC-DC convert applications, which are used along with PV inverters. So let's take an example, a 50 megawatt project in a location where you want to have a DC-DC converters. So why DC-DC converters are key for nowadays is the battery prices is coming down drastically, and DC-DC converter applications are mostly used on the energy applications, not on the power applications. Mostly it's on the energy applications. Energy applications means 1 hour, more than 1 hour of storage, minimum 2 hours to 3 hours storage applications. So that you will feed the PV instead of daytime, you will feed at the night time or the evening time, where you get higher tariff. Or in case of limitations from the grid, you are not allowed to feed so much of power. You will store the excess power to the batteries, and then you will use it. That's what the key for the DC converters. So DC coupling or AC coupling both started at the same time, and but actually DC converters are more you can say it is more experienced, because the DC converters are very common in the drives industries. Okay, so in the same DC converters typically used also for these applications. The plant controller, the battery, the inverters, all will remain same. So only difference was initially, like 5 years back or 10 years back, when the step of the battery storage application started, it was all started for the grid support applications. So grid support applications are always power applications. Power applications means you will have battery storage only for 30 minutes, and there is no PV. It's only the battery near to a substation installed to support the grid in terms of frequency regulations or something like that. So then there is no point of DC-DC coupling into coupling is used, and the battery prices are very high. Now, in that the battery needs to be higher, fast, responsive. But when it comes to the energy applications, where I told about DC-DC convert applications, where you store the energy and you feed the later stage, so that's called energy applications. in the energy applications, you don't need a faster response batteries. So, and nowadays the LFP batteries are leading in terms of electric vehicle industries, and that's where the LFP batteries having a good supply chain and availability with lesser cost. And LFP batteries are very ideal for the energy shift applications. So the battery prices are low and the availability of the batteries are there. So that is pushing the market towards the energy shift application, and that will drive further towards DC-DC converters. So there is no limit on using DC converters in terms of energy for the energy shift applications. So our DC converters from SMA typically is around 500 kilowatt is a one DC converter, and you can connect 6 DC converters to one PV inverters. Okay, so PV and the battery all both will work in parallel and connected to the substations. And we also have two types of DC converters for 1000 as well as 1500 volt battery applications. So this is an example to show you the difference of DC and AC coupling. So this is the DC coupling applications where you will see there is a PV inverters installed with the PV modules and connected to the transformers. This is the existing picture. Now, if you want to add the batteries to the same PV inverter, then you will install the DC-DC converters very near to the PV inverters. So we need some space. Okay, so we need some space to install the battery as well as DC-DC converter on the same locations near to the inverters. Maybe 2 to 3 containers you have to place it near to the station, so that much space should be there. And DC-DC converters are outdoor devices, so there is no difference over there. So the power cable will go to the PV inverter. So PV cable as well as battery cable will be merged through the DC breakers inside the PV inverter, and then it works parallelly and feed the power to the grid. So in terms of grid limitation, the excess power will go to the battery, and if in case of grid demands more power than the PV capacity, the extra power will come from the battery because the PV power is lesser. It cannot support that much to the grid. So in this picture, you can very clearly see that there is no need to have extra transformers, extra RMU. So it will completely save the cost on the AC side balance of systems. On the other side, for the AC applications, you will see batteries are directly connected to the battery storage inverters, semi-central storage inverters directly to dedicated transformers, dedicated RMU. So this is an AC coupling, this is an DC coupling. It is all can be connected to the same grid with the same controller. Our plant controller will remain same for both the cases. It is all same. So in terms of experience, in terms of applications, in terms of experience, in terms of, for example, if you ask me, okay, which is good, or if I have to go for a DC coupling, how to select it in terms of experience. So there is no difference in terms of experience, only the application matters. Okay. So this is how the DC-DC converter will be connected to the each inverter. So here you will see it can be 1, 2, or 6 also. All connected in parallel. Each inputs will have fuses connected to the PV inverter in parallel to these connections. It is very simple. So now, if you want to add, if you're not sure that today how much the battery is needed, but you want to secure your PPAs, like for a in future if there is any grid limitation comes, how to safeguard it. So you make a PV plant design to just provide a space and buy the PV inverter with the provision for connecting the batteries in later stage. Okay, and once after 5 years or 6 years, if you have any requirement to connect a battery because of a better energy tariff, or the battery prices also comes down drastically lower at that time, then you can simply connect it by the DC converter in the batteries and connect it to the inverter. So only requirement is very simple. Provide the inverter with a provision for connecting the DC converter spaces and as well as the space, mechanical space available around the inverter station, so that you can install the battery as a DC converter. So no special engineering is needed. So no additional cost for you except the space to be provided around the e-stations. So this will help you to safeguard the investments in terms of uncertainties. So like this. So you can buy the inverter with the provision for connecting the DC converter, and later you can buy these fuses and the DC converters later once you go in, when you're going to install it. So it depends on the project whether if you're using 1000-volt or 1500-volt DC converters. In case of 1500-volt batteries, you can use 600-volt, 600 kilowatt application of DC converters. If it is 1000-volt application of battery, then it is a 500 kilowatt DC converter can be used. And initially, like some years back, when DC converter was there, the efficiency was very low. But now, due to the present technologies and technologies, the DC converters are more efficient. So here, the efficiency you can say average itself is 98.2. So with the DC couple applications, you will get better energy savings simply because you are avoiding transformer losses, cable losses, and MV system losses completely, including the cost. So in terms of energy efficiency, DC converters are much better, but you have to decide which type of applications and why you should install this storage. And then we can select whether DC or AC coupling systems. Okay, the last one important topic is a hybrid controller, which is the brain for the entire application of the PV storage, diesel, everything to be connected in parallel and to operate. This is hybrid controller we launched in 2011 for the first PV as well as diesel applications. We call it as fuel save controller, and then we step by step develop with more advanced function, including the battery integration of it through storage systems. So it's a proven product. It's been used all over the world for many different applications for both power and as well as the energy saved applications. Time-based tariff, everything are possible in this. So some of the basic example cases hybrid controllers are used are for microgrid applications. Where you will have actual grid. Sometimes it will not be there. Decisions will be there. Maybe it acts as a backup if you add storage, or sometimes it works always in parallel with the battery as well as the PV inverter. So, and the second important application is the grid services. So here, grid services is always be a AC coupling system because there is no PV, and this is how the storage started first 5-6 years back. To support the grid in terms of frequency regulations, response time, just to provide certain voltage supports and everything. And the present way of doing is the renewable energy integrations. Usually the energy shift applications are power smoothing applications, where the DC coupling will also be used. So here we will have PV, battery, as well as the grid. So first we'll talk about microgrid applications, microgrid management applications. So this is one of the first projects we did on a large scale in Caribbean islands, where you can see the PV inverters, PV stations are installed in the first year of the project, and it was working with the diesel gensets. So there was no battery. It had happened in 2016-17. Started with the applications. So both were working in parallel with the hybrid controller. It is an island applications. Later, once we had an idea of the load profiles, and once we studied that how you can optimize, then we added more additional PV inverters after 1 year of operations, and then we introduced storage applications also in parallel with the same hybrid controller. Then a complete system was on, and we were able to switch off the diesel gensets. So before this application, the complete island was powered by the diesel gensets. Now the islands are powered by PV as well as the battery in parallel with the gensets. In case of PV battery is discharged, then the diesel will kick in. Otherwise, the diesel will be in off mode. So following functionalities are used in this project with the help of hybrid controller: the spinning reserve management, genset load management. So PV hybrid controller also talks to the genset controller in parallel over Modbus TCP IP for the fast response time, and the reactive power management, so that DC gensets don't take full load on the reactive power. PV inverters or storage inverters will also take the load as a reactive power to compensate the manage the load completely. Energy shift applications, RAM rate control and RAM rate up and down. So in case of sudden up of the sudden okay, there's a cloud pass suddenly, then the PV generation drastically goes down. Then the battery will come into the picture to provide stable power. And then the last one is the diesel off mode, where the diesel will be completely out of the picture, and the battery inverters will provide the grid for the operation of PV inverters and as well as the load management. The other applications, in case of grid services as well as renewable energy services, the common factors are the grid forming, renewable energy management if we have PV or the wind, are both also possible. Frequency stabilization, voltage stabilization, as well as black start functions. So these are the common functions used in the grid services as well as renewable energy services. So this is our SMA's complete portfolio for large scale applications. So for the products what we see today are used for a bigger capacity projects, not for the home or as well as not for the commercial or industrial applications. For the where you have the bigger capacity of transformers, high voltage systems are there. So these are some of the projects that we installed globally. And in terms of experience, as I mentioned earlier, we have more than 4 gigawatts of experience in terms of storage, including grid forming, power smoothing, frequency regulations, in all type of projects are being used with the SMA storage inverters. So it's time for question and answers. So let's check the questions.
Thank you so much, Ajay, for this in-depth information and sharing your knowledge. Now, I request Priyamada Pandit, our technical expert and moderator for this session, to answer the questions received from the attendees. You please, over to you.
Yes, thank you. Hello, Ajay. I will go through some of the questions that we have received.
Okay.
Yeah. So the first question, it is basic. They want to know a basic difference between the application of grid forming and grid support battery projects. So how do you differentiate what is the main difference in these projects? When do we say it is a grid forming, and what differences are there in the grid forming and grid support projects?
So this is one of the important topic to be seen before we decide the storage. So it all depends on why you want to add the storage or why you want to add the PV as well as storage into the picture. So grid forming means you will remove the main source like BS inserts or the main grid from this, and it will allow storage inverters to form the grid. So that is the first criteria of the grid forming. The storage inverter will form the grid. So it will act as a master here to create the grid at all, like a substation. The second application is the grid support. In the sense, the master is always a main grid or the DC sensors. The storage inverter will act as a add-on, like for example, just to provide additional power in terms of fluctuations, power smoothing, frequency response, or as well as the reactive power support. So these are support applications which works in parallel. So based on your requirement, you can decide it. So one simple thing is, in paper it looks like grid forming is always much better. If I'm getting it, I can completely eliminate it. But grid forming also comes with a lot of additional material, additional components, and additional tools into the project. So the cost of the projects will also go higher. Until unless you really see a benefit, you are sure that grid farming is needed, it's a commercial benefits are there, then you decide on the grid farming. Otherwise, grid support is a common application to start with, and then later you can convert it into grid farming systems also.
Okay. Thank you. Then there is a question regarding comparison of DC coupled system and AC coupled systems. So which technology is better, and is DC coupled a new technology compared to AC coupled?
Okay, so this is the usual questions asked in all the usually asked all the discussions, because DC coupling was not discussed like 3 years back. We are discussing now, but AC coupling was discussed from like 5-6 years back also. It is all because of the applications. The application initially demanded the power shift application, power response applications like grid support applications. So there, only AC coupling matters because there was no renewable energy integrations. So and now the battery prices has come down, which has opened up the market for more renewable energy projects like renewable energy integration services, grid like separate tariffs, time-based tariff supports like evening. We will feed more renewable energy to the grid to get better tariff. So applications are changing because of the battery price changes and the technology changes. So when the grid support applications, grid farming applications and everything, there the AC coupling will be there. But if it is a renewable energy integration projects, because there's a PV, the DC coupling makes more sense in terms of energy applications. So in terms of experience, both of them are same because the same inverter, same controller, same battery, everything will be same. So only difference is how it is placed and how it is managed. So there is no way to say, but DC coupling is getting more aggressive or more getting common nowadays.
Okay. Okay. Next question is regarding the battery technology. So is there any specific technologies which are used for specific applications? Say you have to use some specific battery for power technology or one specific for energy shift application. So, or you can use any batteries. How do you select batteries depending upon the application?
Okay.
Yeah.
Yeah, got it. So for example, if the storage projects are used for the grid services like frequency response. Okay, so in this case, the battery also needs to respond. Like how we seen the response time of the inverters, like 200 milliseconds. That is applicable for the grid services projects. In terms of frequency dip in the grid, the storage inverter needs to respond and provide the frequency within a millisecond duration. This is possible only by high response batteries, which are costlier. So these are typical lithium-ion batteries. So this is a different battery. Now, when it goes to the renewable energy integration projects like DC coupling projects or energy shift applications, time-based tariff applications, there you don't need to have the millisecond response time because there is always a PV as well as renewable energy to stabilization of the projects. So there you can use energy batteries which are lesser costlier than power batteries, power application batteries. So depends on the project, the battery suppliers will provide you with which batteries are suitable.
Okay. In continuation to that, there is one question which is asking: are there any specific makes which are compatible with your system?
Yeah. Okay. So in SMA, there's a communication channel running between the storage inverter as well as the battery BMS. So we always continuously keep adding up the more latest battery technology into the inverter. So at present, whoever is supplying the batteries for the large applications, you can say all of them, mostly all of them are compatible with SMA inverters. If somebody new comes up, please share the requirement with us, including the battery information, then we will confirm. So whoever is the big brands you say in the batteries, everybody is compatible with SMA for now.
Okay. Thank you. So next question is grid farming with battery backup solution, is it also viable for industrial systems? See, because right now we are talking about large scale utility, but can we use the same type of projects? Are these also viable for the industrial applications?
So, okay, for example, if you have a factory where you see a lot of power cuts over there, like 1 or 2 hours a day and everything, then you will always think, why can't we use grid farming system with the storage to get stable power? But for now, the grid farming as in the battery price are very costlier systems. So it has not been evaluated for the industrial applications. If you're getting if you're having a project where there's no grid at all completely, and you're producing a product where which is having a more revenue streaming, then it makes sense. So you have to see a project specific evaluation, but in general stand, it is not viable at present to go for industrial applications because there is a simple solution available. Is a DC gensets plus you can integrate 60-70% of the system with the PV. Only 30% you can compensate with the battery. So that, but for 30%, the cost of the battery will be goes much higher. So that will remove the viability.
Okay. Understood. So also, can we add battery at the later part? So say there is a PV and diesel hybrid project with diesel generators, and you are using PV along with that with some kind of controller, everything. And afterward, you want to increase, say, self-consumption. If you want to increase the PV, can we add battery part later?
Yes, it is completely possible. Only thing is you have to make sure is the communications are done and the spaces are available. Communications are always modbus TCP/IP between the entire network. There is no RS-485 is used. Plus, the space should be available near to the inverter. If it is DC coupling, the space should be available near to the PV station. If it is AC coupling, then the space should be available near to the transformer or the substation areas. But it is possible because the hybrid controller, if you're used from SMA, the same hybrid controller will be used also for the energy storage applications. So they simply add the licenses for storage and use it.
Okay. So for next question, I'm actually coupling couple of questions.
Okay.
So there is one question. We don't have a load profile, but load capacity is 3 megawatt, and we want to use PV plus diesel plus battery. How do you check the battery financial viability? There is another question which says that we have for say 50 megawatt AC LSS solar farm project. How do we decide the battery size? So designing of the battery, how do you calculate and what are the factors that you consider?
Okay, the first important important information needed before buying the battery is a load profile, because the load profile will define how the charging and discharging mechanism is going to be there for the batteries. There is always a depth of discharge. How many times, how many cycles you use in the batteries, that decides the life of the battery. How many cycles from that you use it. So if you use it lesser, then the battery life will be more. So it's all kind of warranty. So the battery manufacturers will always ask you to give the load profile for this. So in the first case, if you're not sure, if for example in case of 3 megawatt project, in simple way is to start with this PV plus diesel genset hybrid systems. Start using it with the 60% of the load profile. So if your load is 3 megawatt, on the 3 megawatt, 2 megawatt, you will add PV and use the hybrid controller and let the system start running, let it work completely for 1 year. And at the same time, the system will start collecting a data, how it is, and then you will know how much energy can be further utilized with the renewable energy by using the batteries. Where SMA will definitely help into that. We have engineering services to see the viability of this, and then we will recommend you how much is the battery can be added or whether the battery makes sense or not. That can be studied, and then you can decide it. But definitely you can 100% start with PV plus diesel hybrid system, and that is all viable. And this type of projects are already started 10 years back. So now with the increase in the energy tariff going on, so definitely it makes more viable for now.
Yeah.
And
so yeah.
And for the 50 megawatt project, first you have to decide why you should go, why you need, I assume that's a utility project. So you should know why you should add storage. Like for example, in case of grid failure, you want to add storage, or in terms of energy shift applications, like if you're going for a time shift application, like if you're feeding the energy to the grid at the evening time. So depends on the application, we can help you whether to go for a battery storage or not, as well as which type of technology, DC or AC coupling. DC coupling is most sense for this type of 50 megawatt projects, but the space should be available, and inverter should have provision for connecting DC coupling systems.
Thank you. There was another question regarding which software you use for all these calculations. So there is no one specific software as such. You have to use, for example, if you are using PV, you have to understand the PV generation. You can use whatever, say you are using PV-Sys or some other. For battery calculation, as Ajay was mentioning right now, you first have to understand the requirement, and accordingly your battery sizing and everything would be calculated. So there is no one such universal software which will give you the battery calculation for all type of applications. If it is only for, say, energy shift, calculation is little easier, because you want to understand, you want to store how much energy, that number, and accordingly you will do that calculation. But it is for the grid support activities, as Ajay was mentioning, you need to understand what should be the response time, what should be the current, how much power and energy needs to be delivered in what time. So there you will probably require manual calculations as well. So Ajay, if you want to add anything to it, if there is any specific software you can suggest to the customer.
For complete design, for the complete plant design for the battery storage, we don't have any dedicated software. There are software specific Homer, but it's a combination of mix, PV-Sys, Homer, MATLAB, everything will be used in parallel by the different experts, as well as the battery manufacturers also have their own tool to study their battery performance once you provide the load profile. So you have to ask each and every suppliers to provide the information, and they will provide you that information. And as the battery technology keep changing, so these tools will be keep evolving or keep changing it also.
Okay, there is one question.
Piyush, sorry to interrupt. We have already running out of time. So I request everyone who still have some question, we can still address few question. We can extend the session by 5 or 10 minutes more. And those who want to stay back, they can stay back. But thank you so much for all your participation. And we already shared in chat box our service contact details, our Sales India and Sales Southeast Asia email ID. So you can drop in your queries. If you have any queries, you can drop into those email addresses. And we're extending the session for others. Yeah, please continue.
Yeah, so there are many questions. We still, even if we extend, I don't think we'll be able to cover all of them. We'll try to cover as much as possible from different areas. We will try to cover. So one of the main concern is, just a second. Yeah, so can we change from grid following to grid forming seamless without any stop? So basically, if suddenly the grid goes down and your application is to provide the backup, so will there be any blackout between, or any interruption in between at the load side?
Okay, so now if the project itself is designed as a grid forming system, then it can do that. So in case of grid is available, it will act as a grid supporting applications, and then in case of grid failure, it will convert itself into a grid forming system immediately. It will like 30 milliseconds or less than 100 milliseconds. There will be a difference, but it's not a big problem at all. But if the project is first designed as a grid following, and then it needs to be converted into grid forming, then it needs some upgrade in terms of system design. Some changes may be necessary, but it is possible.
Okay. There is one question. How many hybrid controllers are needed in 100 megawatt solar plant?
So okay, so if you're using I assume 100 megawatt, you will use large scale inverters, either PV or as well as storage inverters. So each hybrid controller can talk to 200 inverters. So if you're using 4.4 megawatt inverter of PV, it's only 25 inverters. And in parallel, if you use DC converter also, it will not count that much. So one hybrid controller will be more than sufficient.
And there is one question about, can we have the possibility, I mean, there are multiple questions, I'm clubbing it together regarding the possibility of how the batteries would be charged. So whether there is a possibility of charging batteries from PV modules, wind energy, or grid, or there is also one question who want to charge batteries with generator. They don't want to use the grid power, and whether it is possible to charge batteries with generator power.
Okay, so the source can come from the AC side. So either it can be from the wind DC sensors or from the grid. It is all possible. Okay, so from AC, either it is from the DC coupling or AC coupling, it is possible. So you can charge the batteries from the sources. Now the economics has to be there, that whether you can charge from the battery, charge from the grid or from the DC sensors. So this logic can be defined. So if the grid power, only grid power is available, then don't charge the battery. If DC sensors are on, to charge the battery. This kind of logics can be defined in the hybrid controller and customize it. But in general, it is possible. Only thing is you should be having economics calculations for all this functionalities.
Yeah. Do we have time for a couple of questions, or we still have time, right?
We can just, you can take 1 or 2 more questions. That's fine.
Okay. So there is one question: does the auxiliary transformer need to have a dedicated feeder from the grid, or it can be coupled on the main storage feeder? Basically, what happens if the grid goes off? This is from the redundancy point of view.
So let's take okay, in the storage applications, if it is a grid supporting applications, then it doesn't matter, because if the grid is off, the auxiliary can be off because the inverter will be off. But in case of grid forming function, then you need to provide a black start function required for the transformer to start. So then in this case, we will provide a separate guidelines for using the external auxiliary power. The inverter have a different option for connecting the auxiliary power. So that auxiliary power will be provided through a UPS power supply. So it will be used for starting the inverter and to provide the inverse current required for the transformer to start.
Okay. There is it possible to provide ramp rate control and other grid support functions done with BESS and PV without the hybrid controller? We are concerned with the developer costs.
Usually this hybrid controllers are usually installed on the plant level. So the requirement is always this ramp rate control or this kind of grid services to be monitored at the plant level. Only from the inverter it can still do the ramp rate control at the inverter terminal level, not at the after transformer, not at the after transformers. So in some functions at the inverter level it is still possible, but it does only at the inverter level, not the plant level. But if you need more advanced functions, then you definitely need hybrid controller to tell the inverters what should be done. So if you have any specific requirement of the project, please write it to us. Then we can evaluate. So there are some projects are there which are done without hybrid controller because it was needed only on the inverter level. But it's a very, very small applications or special cases.
Another question of grid operators are very concerned about the ability of grid tied BESS system to provide synchronous inertia in real time, sub half cycle response time, in order to support grid with significant renewable penetration. So basically they want very good response time when with increased renewable penetration in the grid. Is this functionality available yet? And if not, how long will it take for this functionality to be available?
This is actually already available. We already have the earlier test projects are running in Europe, and our biggest project is 100 megawatt project with RWE. which is to provide grid inertia supports. So if you have any special requirements, specific requirement for a support, we can just write it to us. We will provide. Our storage inverters are already compatible with grid inertia supports, and it is synchronous generator. Whatever it can do, the same our storage inverters can do perfectly.
Any last question, Piyu? We can just take any last question.
Yeah. The last question, it's kind of comparatively a simpler one. In a grid forming, if you have multiple inverters, how does all the inverters synchronize? So basically, who would be master and how it will work? Yeah.
Hybrid controller will always a master here. So in storage applications, it will decide. Okay, so it will always tell the inverters. So the sequence will be like inverters will start step by step, one by one, and it will provide the transformers, because you cannot start entire system immediately. So it will open the load network, and then it will start the line, and then it will keep providing the supports. But this is I'm saying about a big project. If it is one single system, then it is like an immediate support systems.
Yeah, so typically, for example, it is a 100 megawatt system. Not all inverters would be grid forming. There would be a few inverters with battery. There will be other PV inverters. So some of them would be working as the following followers, and some would be the grid forming ones.
Yes.
Setting the voltage and frequency references. So and the hybrid controller will obviously coordinate with all of them. So that's why it will be the master.
And important thing is this needs a precise engineering. Through our engineering services offering, we provide simulations as well as different scenarios to see this, how many inverters needs to have this like initial support, or in terms of black start functionalities are needed. So this kind of study we can offer to the customer before going further with the project executions. Then they can implement the project successfully, and we can also verify that after the commissioning.
Yeah.
Okay.
So one of the biggest grid forming applications is in the execution stage in Australia with a 250 megawatt project, where the 250 megawatt will be forming the grid, where we SMA inverters up series inverters are supplied for that.
So there is one question immediately I say, so does that mean there will be only one inverter will work as grid forming and others will work as following?
Not really, because we should see that how much is the inrush current needed for the entire station, and how much the startup power is needed. Plus in case of sudden disconnection of the PV, then this load needs to pump in to support the loads. So there are calculations. There's no defined number like 10% or something like this.
Yeah.
We have to see a scenario how the load profile, whatever loads are connected to this, and then we can decide it. But in usually how much more you add, it is more better to in terms of reliability, because sometimes the transformer line network trips for the dedicated transformer. Then something else has to start so that it will power up the line. So you should also have redundancy also included in this.
But in short, just to summarize all the discussion we had, in storage applications, typically for the large scale storage, your every project is going to be different. 150 megawatt project at one location can have different requirements than other project. So there is no standard design guideline or standard. There are guidelines, I would say rather, but there is no standard template that you can use. You have to understand all the scenarios, you have to understand all the applications and design your system, and that's why it is very important. We also understand the importance, and that's why we also provide support from designing point of view as well. So if you have any kind of projects in this area, please drop down, contact us, drop down an email. We have given all the contact details. You can see Ajay's email address. It is showing on the screen as well. So you can contact us by any means, and we'd be more than happy to help you with understanding your requirements, and then accordingly we can suggest the best suitable solution for you. So I think that's
thank you Ajay. Thank you Piyu. Thank you Ajay for in-depth information, and thank you Piyu for summing up it nicely. And we have already shared the contact details. So there are many questions still coming up on screen. Thank you so much for your patience and for all your participations once again. And with this note, we can conclude this webinar. Thank you so much. Have a wonderful day ahead.
Thank you, everyone.
Thank you. Thank you.